the interaction of two-level atom with a single mode radiation. Today, I want to discuss about probability amplitude method. We have two types of methods. One is the probability amplitude method and the other one is the density matrix method. And first, I would like to discuss about the probability amplitude method. And here we have a two-level atom with energy levels A and B, and this interact with a single mode of radiation, which has frequency nu and E of t as the electric field. Consider a two-level atom where the state will be. The state for this two-level system, because this is in the superposition state, so I can write the state for this system as this is the state Ca of t, A, Cb of t, because this Ca and Cb, these are the probability amplitude and this depends upon time, and this shows that how this Ca and Cb evaluate with time. And the goal is we have to calculate Ca and Cb. So this is our goal in this whole process. To calculate this and this, we must use the Schrodinger wave equation. And this Schrodinger wave equation as H psi, which is equal to iota. This is the time dependent Schrodinger wave equation. And where H, which is equal to H naught plus Hi. And this is the free part. This is known as the free part. And this is the interaction part. Of the Hamiltonian. Next, H naught. We use a completeness relation here. Completeness relation for this two-level atom is AA plus BB, which is equal to 1. So this is a completeness relation. Now, using this completeness relation, I can derive the free part of the Hamiltonian for this two-level atom. How? Because we have one here, one here. I can replace this with completeness relation, which is equal to 1, and this value here, AA plus BB H naught, this one, and also here is 1, then I can replace 1 by this value. Okay. Now, we can take this, this, and this, 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 and this. So we have 4 terms, A, H naught, A, and plus AA H naught in this term, B plus this with this, so B H naught AA plus BB H naught and BB. Now here you can see H naught can operate on this state, this one. This H naught can operate in this H naught can operate on this, and this. And we can get some type of this. If H naught operate on A, then it gives us some eigenvalue with related, some eigenvalue related to this state. So this is EA and A, and H naught operate on B, then it gives us some eigenvalue of energy EB with this state B. Then we proceed. This can give us EA, this EB, this gives us EA, and this gives us EB. Then this is EA. We can take this outside from this relation, and we have EA, AA, and this A, and here EB, AA, B, plus here EA, BB, AA, plus this term EB, B, and B. You can see here, these are orthogonal state, and these are this and this, the orthonormal state, and this, these are orthogonal states. So this state goes to 1, this state goes to 0, this also equal to 0, and here this state equal to 1. So we have EA, AA plus EB, BB. And where we know about E, which is equal to h cut omega. So this is the relation we already know. So if EA, this is equal to h cut omega A, AA plus h cut omega B and BB. So this is the relation, free part of the Hamiltonian of two-level system. Now, if we have three-level system, and for this, let's consider we have a three-level system, some C state as well. Then H naught, the free part for this Hamiltonian must be equal to h cut omega A, AA plus h cut omega B, BB plus h cut omega C, CC. And if we have a 4 level, then we will have some another term, and so on. Now consider the interaction part of the Hamiltonian HI. Here HI, which is equal to minus E, if we take this as a one dimension, EX and E of T. This is true because if you have a system like this, if you apply an electric field, then the shape of this system must be like this. And here you can see some displacement, and you can see the positive charges and the negative charges separated from each other with a distance d. And we know this thing is the dipole moment, and dipole moment P, which is equal to Q D. Classically, we can consider just like this. Q is the charge on the particle and D is the distance between this. Now, if we apply this electric field, the same thing can occur here. This E is the charge on electron, and this X is the displacement. But one thing is must be clear about here. We can see that if we have two charges like positive and negative charge, and this is a distance d, then we have a dipole moment between positive and negative charges, and we can represent this in a qd. But here we apply the electric field between two levels. So just like positive and negative charges, you can't see here the dipole. Then how we can get the dipole moment like this? The point is, if here is an electron and this field excite this electron here and it reaches to this point, then here you can see a hole, and this hole can behave like a positive charge, and this is a negative charge. So negative and positive make some dipole between these two levels. So this is the point that we can have some dipole in these two energy levels. So this is the resemblance between this and the energy levels. Further, we apply a completeness relation, and this completeness relation is minus Ex minus E, and this E I can take out like this, and AA plus BB and X, and similarly A plus BB. So this is equal to 1, this is equal to 1, you can get this thing. Now solve this equation further. Minus E of t. We have some four terms, this, and this. This is very simple. X, A, plus this, and this. A, X, B, plus this, and this. B, X, A, and plus B, X, B, and B. Now here this is very important thing. This one, this one, and this one. This is the expectation value. The expectation value, actually the average value of the average value of the displacement, distance d. So AXA, the average distance between A and A. So logically this is equal to 0, because if I construct some dipole like this, and it has some distance d, so we can say that this is the average distance, it have some average distance. But if this charge come near to this, and the average distance becomes approximately equal to 0, then we can say that like this, A and A means this level and this, that the average distance of this level, so it means that it will be equal to 0, because there are no average distance between the same energy level. So this point is clear that this will be equal to 0, and this will also equal to 0. And we have Hi, which is equal to minus Et, and we have AB and X. This is A, this is B plus B, B, X, A, A. So this term AXB, this is the average distance, and this will not be equal to 0. Now apply this E. I can write down this minus E, and this is the average distance. This is the average distance. So I can represent this average distance by X, A, B. This is the average distance. I can represent this like this, and here A and B minus E X B A. This one, this is the average distance X B A and B A, and we have E of T. Now we should look to this term. This is very important term. This one and this one. And we must compare this term with this, the classical dipole, this one. Here, the dipole, which is equal to charge into distance. Here, the charge into average distance. So charge into average distance and charge into distance. So this is the same. And we can call this EXB. This is the dipole, just like this. And this dipole minus, I can represent this PAB, AB minus PBA, BA, and we have E of T. and the recent book, Scully and Zubiri book, this dipole moment PAB is also represented by like PAB. So this is just a symbol. You can represent a dipole moment by this or by this. So this is the dipole matrix element. We can say that this PAB and PBA, this is the dipole matrix element. This is known as the dipole matrix element. Dipole matrix element. Or it's also known as electric dipole moment. Electric dipole moment matrix element.